All right, let's get started. We're happy to have Raphael Flauger here today, a person who might not even need an introduction already by his age, but maybe some of you don't know who he is. He started his career in Austin under the supervision of Stephen Weinberg. After that, he moved on to Yale as a postdoc, and then he continued his postdoctoral career at a joint position at the IES and NYU. And then in the in the fall of last year, he moved to become a faculty member at Carnegie Mellon, and within a year, he decided it was good to move back to Austin, so now he's faculty at Austin. Raphael has worked on many different problems, ranging from string theory, models of string theory, leading to inflationary background, condensed matter physics, lattice quantum field theory, and actually I would say that he's been mostly known in recent years for his cosmology work, in particular the stuff that he's done on the Planck reanalysis together with David Spergel and René Losek in 2013, as well as his work on the BICEP2 data and his proof that most of it is probably dust, and that was later confirmed in 2013, 2015. So it's a pleasure. Go ahead, and Sprout is going to talk about something very similar.
Okay, thanks for the invitation. It's actually the first time I'm at CITA, and if one doesn't count times I passed through the Toronto airport to go to Perimeter, it's also the first time in Toronto, so it's really great to be here. Also, thanks for the introduction, and yeah, so a lot of it will, you'll see, a lot of the things that Dan mentioned, you'll see in the talk. So I thought, given that we've been celebrating the 50th anniversary of the publication of the measurement of excess antenna temperature, or the detection of the CMB by Penzias and Wilson, and the interpretation of the measurement in terms of cosmic black body radiation by Dickey, Peebles, Roll, and Wilkinson, I'd say a few words about the history of the CMB. I think this part of the history is well known, and I don't have to say about it, so I just wanted to highlight two quick things that are maybe not not mentioned or appreciated as much as perhaps they should be. So as soon as you claim that what you're seeing is black body radiation, there's obviously a number of things you have to confirm. The first one that comes to mind is you have to actually check that it's a black body radiation. This measurement was at a single frequency, and people set out to do this from the ground very early on. And then, of course, everyone knows the famous measurement by the COBE satellite and the FIRAS instrument in particular on the COBE satellite by Mather, which led to the Nobel Prize. There was also a measurement, and maybe it's known here because it's a Canadian experiment, from the COBRA experiment led by Herb Gosch, Mark Halpern, and Ed Wishnow, who also had a very nice measurement of the black body spectrum. And this was within a few months of the FIRAS measurement, but it's typically, in many places at least, it's forgotten. So I wanted to point it out also because I think it's remarkable that it was done by 3 people. And you should also keep in mind that both of these groups were working on it for 15 years. So it's not something that you could have just reproduced in a month. So in a sense, it was unlucky that they were a few months late. The other measurement I wanted to point out is something you also have to really test right away. So if you have this cosmic black body radiation, it's unlikely that we're at rest with respect to it. So you expect some dipole from the motion with respect to this radiation. People looked at it very early on. In one of the experiments, so one of the measurements I really like is the one by Paul Henry, which was the first measurement, I would say, of that measured the declination, right ascension, and the amplitude of the dipole. So, and as you can see, it's a single author. He built the experiment, launched the balloon, took the data, analyzed the data, and found a measurement that's still consistent with what we know about the dipole today. And this was his PhD thesis, which is definitely cooler than my PhD thesis. So this is also a nice measurement that's not mentioned too often, so I thought I'd mention it. In addition, of course, you know that you see all the structure around us, so you don't just expect the dipole, you expect anisotropies on smaller scales. I won't say much about the history of those. I mean, as you know, they were also measured by Kobe and relict. But I'll skip straight now to the Planck data, which is a huge step forward from what I just showed you, of course. So you have very nice data here. Gray, as you know, is the data. Blue is the bin data. Red is the model. So it all looks very nice. There's some minor glitches one can maybe argue about, but it's a really nice measurement. One thing I wanted to say, just because sometimes we were quoted as saying that somehow there's an issue between Planck and WMAP, is that Planck and WMAP temperature really agree very well at WMAP resolution. This is something I'm trying to show you here in a visual way. One can also do it in a more quantitative way. What I'm showing you is the WMAP W band, which is centered around 94 gigahertz, and the Planck 100 gigahertz frequency map. And I'm smoothing the WMAP maps with the Planck beam, the Planck maps with the WMAP beam, so they're really at the same resolution. And if you look at high latitudes, that you'll see that they agree very well. So you see the same structures in both of the maps, just like you should. I should also say that these are shown at N-side 512 for everyone who's using heel picks. That means something. For everyone else, it probably doesn't. In practice, it means that you're chopping up the sky into 3 million little pixels. So this is what these are. And then if you look along the galactic plane, you see that they're actually slightly different. And at first, you might be confused about it. So what you see is that there's a little bit more red here that's missing here. There's more red over here than over here. This part is redder in Planck than in WMAP. So you can look at the difference, and you see that the difference looks like this. So you might wonder what this could be. And you should keep in mind that these bands, this is not really measured at a single frequency, but it's a range of frequencies around 100 gigahertz. This is a range of frequencies around 94 gigahertz. Foregrounds typically very smoothly, so you wouldn't see the difference necessarily in these two bands, the typical dust or synchrotron. So the only thing that this can be is really, as you see, there's more emission in Planck than in WMAP, so it has to be a line emission that's in the Planck data but not in the WMAP band. And in fact, there's the CO emission, and you can make maps of CO emission in other ways. I can discuss a little bit more how these maps were made, but you see that essentially really what you're seeing here, this difference really is the CO line. So in that sense, the maps agree very well. One should also keep in mind that Planck is really much more powerful. One way to illustrate it, I've tried here, is just to increase the number of pixels in the sky. So the previous ones were at 12 million. These are 3 million, sorry. These ones are at 12 million pixels. And you see that Planck still looks very nice. WMAP is starting to look quite noisy. You can barely see the CMB up here. You can really only see it where it scans the sky more often than in other places, here near the poles. And then you see this little ring. You can still see the CMB, but otherwise it looks quite noisy. For Planck, you can even go to 50 million pixels, and it still looks the same. Now, a more quantitative way to do this is to just show you the error bars on the measurement of the CLs. And for low L, both of the experiments are cosmic variance limited. Planck is cosmic variance limited for the 100 gigahertz channel, roughly out to about 1200. For WMAP, you see the noise coming in, and you see that the error bars on the CL measurement are about an order of magnitude better for Planck, around L of 100, and 2 orders of magnitude better at around 1200. And furthermore, this is not the most sensitive channel on Planck. So most of the information comes from the 143 and 217 gigahertz channels, which have higher resolution and lower noise levels. So, okay. What we've learned from these experiments is that the early universe is very simple, and the data is in good agreement with lambda CDM. This is something that we could have, or these tables we've already seen before Planck, but now we know them with, we can be more confident in them simply because we can allow parameters to be added to the model. So here lambda CDM plus x stands for anything that you might want to vary, like the sum of the neutrino masses, the curvature, the tensor to scalar ratio. And you see that the data always pushes you back onto the lambda CDM value, also if you allow additional things to vary. So the data doesn't really prefer anything beyond lambda CDM at the current point. You can also predict the polarization in the context of lambda CDM, and it agrees very well. There's still some things to be ironed out here from leakage, but all in all, it agrees very well. And lambda CDM, as you know, also agrees well with the low redshift data, both supernovae and BAO data. And so at a first look, everything looks good. And I think this is also really the message you should take away from the talk if you didn't know the message already. But I mean, so lambda CDM really works very well. Also, the parameters between the 2013 and 2015 were very consistent at the level most people care about. I'll now say a few things about them that I think are still interesting, but it doesn't really change the bigger picture that it's all quite consistent. So one of the parameters that actually did change between the two releases is the optical depth. So here, this was from the WMAP data. This is now from the Planck LFI data. And to a large extent, I think the reason for this shift is understood. It's just because we now have a better way of modeling the dust. There was no real dust template available for the WMAP analysis, but we now have a dust template from the Planck 353 gigahertz data. And this was already shown, so this is not an original analysis, this is just my version of it, but this was already in the Planck likelihood paper in 2013 in the Appendix E. You see that if you do the analysis either the way WMAP did it, you use the Ka, Q, and V band, clean them with K band as a synchrotron template, and use the WMAP dust model, and then co-add them, you get the likelihood here in green. If you, instead of the dust model, you use the 353 gigahertz polarization data and co-add the maps, you get the red one. So you get this shift. So this is, for the most part, the explanation. One of the confusions I have, and I don't know if Dick wants to comment on it. I don't know if people are looking at this. I sent emails to, I guess, Marco and Andrea Sacchi. So if you look at the LFI data versus WMAP data on large scale, so this is, let's say, L of 6 to 23, here it still looks more or less consistent, but this includes error bars. So even already there may be something going on. And then certainly if you look on the larger scales, there seems to be some issue between the LFI and WMAP data. So there seems to be some lack of power in LFI or some excess power in WMAP. I don't know which one it is. But in any case, I would say they don't really agree. So this includes error bars. This is, I would say, just means that they don't currently agree. And this would pull tau down in addition to what I just discussed about the dust. I don't know if this is something
so there is I think you probably know this, there is a low-L polarization paper in development.
Okay.
Should out by now, but like all things in Planck, should have been, it's not what actually happens. But it's pretty much converging, so it does definitely supersede what was in the earlier.
Okay, yeah, that's good. I mean, so this means also there's new maps, I guess. I mean, because this was based on the maps that were published, so there's...
The HFI weighs in.
Oh, HFI will be great to have, but this, yeah, here I didn't use any. This is just LFI.
What we released was just associated with 744. So.
Okay, yeah, so this is one of the things that I think is still worth having an eye out. This also, I mean, measuring tau is also important for future measurements because Planck is really the one experiment right now that can do it. In other ways, would be in the future with Lightbird or in other ways with Hera or just things that are not the CMB. But hopefully Planck can still give us a value with error bars that's close to the Blue Book. I think that would help everyone out a lot, but we'll see. The other thing that I wanted to point out, just because this came up at a meeting in Paris that I couldn't go to because I had visa problems, and Dick raised a question about our reanalysis. So there's a shift in NS, I guess, that I think everyone agrees on. So there was a shift between 2013 and 2015. And much of the shift really can be traced to systematics in the detector set maps in the 2013 data. This is something that you can see. So this is not based on, well, it's a plot I made, but it's really just based on Planck data and the Planck covariance matrix. What you can do once you have a covariance matrix for all the frequencies, you can make compute the conditional probability for measuring 217 gigahertz based on the measurements at 100 gigahertz, 143, and the cross spectrum between 143 and 217. And at low L, the two agree very well. At around 1800, there was a discrepancy. So this is just the data that was in the 2013 likelihood code. And then here you see this is now, I think everyone agrees, is due to a Cooler line. So Cooler line means you have the satellite, it spins around its axis around 46 times, then it moves, it spins again, and this happens at about 1 round per minute. The Cooler vibrates at 10 hertz, 20 hertz, 30 hertz. The frequency of the Cooler drifts around a little bit, and once in a while it's in resonance with the scan strategy, and this means you're imprinting features onto the data around 600, 1200, and 1800. Naively, this should appear as an excess, but the effect was known, and there were attempts to remove it. And here, this is a incomplete removal of the Cooler line. So interference between the Cooler and the readout electronics is what caused this dip, and this is for the most part responsible for the shift in NS. In addition, there was excess power here on small scales, partly just because the analysis was based on detector set maps, meaning you're correlating things that are happening on between different detectors on the same spacecraft at the same time, and there's just correlated noise between them that you're seeing here. In addition, there was a bug, I guess, in the code that associated the wrong beams between the individual 217 gigahertz set detectors. So I think the shift is understood and is coming from this. Then, so I think that part we all agree on, that there were these issues. Then the question was, does Planck also see the shifts we were claiming? So here were the analyses we were doing. Here was the Planck measurement in the 2013 papers. And if you plot this year's analysis, it comes out somewhere up here at 0.965. And this is the Plick data. The CAM spec is around 0.968. So we can. So it's true that this didn't shift all the way, we said, but I would argue that this point is closer here than here. And to me, it's still somewhat interesting why there was this discrepancy between the two likelihoods. I don't know if people are still working on it or just have given up on it. It's not really just the shift in NS between the two likelihoods, but there's other parameters. If you look at the foreground parameters, the CIB, for example, is different by 2.7 sigma. The helium abundance is different by almost 4 sigma between them. So there's definitely shifts on small scales, and also calibration parameters. And for what it's worth, the CAM spec version agrees better with ACT and SPT, I guess, which is the one that has a slightly higher NS. The other thing at first sight is that the temperature data and the polarization data agree very well with each other. So if you look at the column here and the column here, there's relatively good agreement. But again, if you look more closely, there's a number of things that one notices. So for example, for the temperature data, the omega matter is the high value of omega matter and sigma 8 that lead to the tensions with the low redshift data. For the polarization data, that isn't really the case. It's lower. Now, there's reasons to trust the polarization data less because, as I showed, there's still systematics issues. But in any case, I think it's interesting that there are these small differences in parameters that one actually somewhat cares about because of tensions or small tensions with low redshift data. Now, also interesting to me in any case, and this is something I've been looking at for a while. I was hoping to have an analysis finished, but I don't, so I can't show you too many plots about it. But the temperature data prefers a high value of a lens. So a lens, if you don't know what this parameter is, it's more of a fudge parameter. So lensing, you can imagine, so if you have a patch of the sky, some lens that magnifies the CMB, it moves the CMB peaks to slightly larger scales. if you have a patch that demagnifies it and moves it to smaller scales, when you're measuring it over the full sky, you get an average and you're smearing out the peaks. So this is essentially what this parameter here is measuring. It means that the peaks are somewhat smoother than you would have expected in the context of lambda CDM. If you marginalize over this parameter, then you also see that you get a better agreement between the temperature data and the polarization data. This doesn't necessarily mean anything, but to me this A lens has been an interesting parameter. There was a paper recently, I guess, where it's associated to changes in foregrounds on small scales. I'm not sure that that's really the explanation, but in any case, so what I've been trying to understand, but I'm not finished with, is to what extent this could be due to the filtering of the time order data that's being done. And I think this would be something still, I mean, hopefully this is something that will be included in the next release. I mean, in terms of simulations. It wasn't included, I guess, in this set of papers, but it would be great to see the end-to-end simulations that include these things. The reason it's somewhat relevant is because there is this tension between the amount of clustering at low redshifts inferred from the Planck data and the amount of clustering inferred from various probes. Here I'm just showing you one of them, the TSC power spectrum, but there's many, many ways. I mean, there's the lensing measurements, the X-ray measurements. There's really a TSC cross X-ray. There's a number of measurements that indicate lower values of sigma 8. All of them individually, you would say, oh, these are difficult measurements, and there's probably large systematics. And this may still be true, but the fact that they're all low to me makes it somewhat interesting. This tension is also, well, in a smaller way, is also there if you compare the Planck temperature data with the Planck lensing. So the amount of sigma 8 omega matter inferred from the lensing likelihood is somewhat lower than the one inferred from the Planck CMB cosmology. And somewhat interestingly, this is not the case if you look at the Planck polarization data, so it's in much better agreement. It's not a big tension, so it's unclear how much time one should spend on it, but I've been spending some time on it, and I've been trying to understand it, but so far.
Sorry, is that the reason tau also comes down in TE plus low EE? I mean, tau comes down in all three of the last three cases.
Yeah.
That's the same effect.
Yeah, I think so. Well, there's no, I mean, there's also, even the low L, we can look it back at the likelihoods, but this likelihood also gives you slightly lower values of tau already. Yeah. Okay, so just to summarize this discussion, I guess, so the cosmology derived from Planck temperature predicts slightly stronger clustering than what is observed at low redshifts in various probes. As I already said, the low redshift measurements are challenging, so it's not clear how seriously one should take it, but there's also these tensions, well, tension is a big word for these small things, but these tensions between Planck lensing and Planck TT, and it's still interesting to me to understand to what extent this has anything to do with the A lens. And yeah, anyway, so that's what I wanted to say about the Planck data. And if you have more questions about these, I can show you more plots, but I didn't want to.
To go back to the issue
Yeah.
of cluster tension and all of that.
Yeah.
You know, some people tried to, with the 2013, were pushing that really it's a higher neutrino mass and that
Yeah.
explains things. And that is not as compelling an argument with the 2015 data. So now the other thing I would point out, Hill and Spergel is, I would say, on the slightly low side, right, relative to recent measurements of the sigma 8 from clusters. So I'm not saying that the problem has gone away, but it relaxed a bit.
I agree. Also, the DES lensing also is closer to Planck now, although it still has pretty large error bars. Yeah, I agree that things are approaching each other. I don't know if that's a.
Going to be a great convergence because clusters are complex systems.
Yeah.
And as you know, we're now in a situation where the different ways of trying to get the masses are giving some different results. results. So it's, still quite a puzzle.
Yeah, I mean, I don't think, I think I agree with you in the sense that I don't think that whatever the tension is, I don't think it's due to neutrino masses. So I don't. Too bad. Yeah, it would be more exciting that way, but it's more likely that it's some systematics somewhere.
Or misunderstanding of the nature of clusters.
Yeah. Okay, so now I guess I'll switch topics a little bit and talk about the very early universe and think a little bit about, or talk about the primordial perturbations. And here what the CMB has given us is really a very model-independent conclusion. It taught us that the perturbations that we see must have existed before the hot Big Bang. They're nearly scale invariant, but not quite scale invariant. So we now have a detection of this departure from scale invariance at 5 sigma since Planck. The perturbations are very close to Gaussian. They're very close to adiabatic. And the big question that everyone is trying, or many people in the theory community are trying to understand, is what generated these perturbations. One interesting question, so the model I'll be talking about in this context is inflation, which I think is our best candidate for it. And one interesting question in that context, I think, is to ask, what can we, assuming that inflation is the correct model, what can we learn about it beyond NSNR, which is one of the things. So the reason these questions also are interesting, I think, is that we'll be able to make, well, they teach us something basic about the problem. What is the energy scale of inflation? It should be one of the most basic questions about it. How far did the field travel? Then are there additional light degrees of freedom? This is something. So these basically you can look for in the CMB. These are the imprints of tensor modes on the B mode polarization. Then there's the question of, are there additional light degrees of freedom? This is something you can look for with local non-Gaussianity, which we can't really do significantly better in the CMB, but maybe spherics is something that can help out with this, or more generally, large-scale structure surveys. And then there's the question of what is the propagation speed of the inflaton quanta. Here you might ask, well, why is this something you care about? But you should care about the sound speed of things. So let's say I give you 2 blocks of material and I don't tell you what they are, and we paint them in the same color so you can't tell by looking at them. If you want to find out what they are, you will probably knock on them or try to measure how fast speed propagates in the medium. And in the same way, in inflation, the speed of the inflaton quanta really is a good way to discriminating between different models. So these are some of the questions, and I'll really mostly focus on these ones because they have to do with the CMB, but these ones are, I think, equally interesting. And so as you know, for the energy scale of inflation, there's also a prediction of the inflationary models that they predict invariance, a scale invariant spectrum of gravitational waves. And the interesting thing is that it's really only sensitive to the Hubble scale, or the expansion rate of the expansion of the universe during inflation, which you can turn using the Friedmann equation into a measurement of the energy scale of inflation. And what you find, if you write it in terms of the tensor to scalar ratio, which is the ratio of the power in tensors to the ratio to the power in scalars, you find that the energy scale is around 10 to the 16 GeV times r over 0.01 to the 1/4. This means, so 0.01 is a good number because that's roughly what we'll be able to detect over the next few years, and it tells you that we'll see primordial gravitational waves in the CMB if inflation happened at the gut scale around 10 to the 16 GeV. The 1/4 is a little bit sad because it means that if it happens even slightly below, we won't really be able to get there. So even 1 order of magnitude here is difficult to do. So an upper limit here will not be too exciting, but hopefully there will be a detection and we have a chance to really learn about the earliest moments of our universe. Now, for the field range, what we've known since the paper by Leith, and there was actually also a paper by Turner independently, we know that for a tensor to scalar ratio large compared to the 10 to the -2, the inflaton must have moved over a super Planckian distance in field space. Now, you might ask why you care, but the problem is that the motion of scalar fields over a super Planckian distance is hard to control in an effective field theory. A lot of you, I think, have heard the arguments. For those of you who haven't, I just still want to go through them very briefly. So let's imagine you have some low energy effective field theory with just one light degree of freedom, just the phi field, and you're interested in energies low enough so you can ignore the higher derivative terms in the action. So you just have a quadratic kinetic term, two derivative kinetic term. Then the only thing you need to specify the model is the potential, and what you might have some constant, cosmological constant. The linear term you can get rid of by a field redefinition. Then it has some mass, maybe some cubic self-interactions, quartic self-interactions, and higher order self-interactions. These self-interactions typically come with coefficients of order 1. These are often called Wilson coefficients. And then here, there's the cutoff of the theory, which is necessarily below in Planck. If you're interested in motions of the field over a distance below the cutoff, then you see that this is negligible and you only care about the renormalizable part of the potential. If you want to move it over a distance that's large compared to the cutoff, one thing you would need is to know all these coefficients. Typically we don't, but you could say, well, maybe someone gives us all these coefficients. Can I then trust the field to move over? Can I then trust my description? And the answer is that still no, because this single field effective field theory you should imagine as arising from integrating out heavy degrees of freedom. And in the absence of any symmetries, this light scalar field will also have couplings to these heavy degrees of freedom, which have masses of order lambda. And so if you have a coupling that's phi squared chi squared, and you move phi over a distance comparable to lambda, then you can have cancellations between these terms and the mass of the heavy chi field. So the mass of the chi field drops below the cutoff. You have to include it in your effective field theory. If you had additional light fields in here, you would expect them to acquire masses of order the cutoff. So the spectrum of your effective field theory changes completely as you move fields of order the cutoff, at least in the case where you don't have a shift symmetry. So this is, I'm trying to illustrate this here. So the psi field is supposed to be the heavy field, the phi field is supposed to be the light field, and then all these contours are supposed to be lines along which the potential is constant, and then you have a potential with a number of minima. Here in this minimum, the psi field is heavy, the phi field is light. You can integrate out psi, you get exactly this kind of potential, and as you move in this direction, so it's a single field model, and in principle all these coefficients are calculable here, but you see that as you move the field over a distance comparable to the cutoff as you get here, it's really a two-dimensional problem, so there's no sense in which you should trust this, and this is what makes this difficult to trust these super Planckian excursions in effective field theory.
And another point
Yeah.
Is flattening, for example, formal flattening, etc., of the potentials, so that you would sort of be somewhat misled by this expansion because there's a denominator which is killing the high terms, or at least some of them. I mean, maybe it doesn't mean you can't protect everything, perhaps, but you know, the issue is what does the effective potential actually do if you go some large distance away.
Mm-hmm. Yeah, so one solution to this is to use a field with a shift symmetry, and then you have only couplings, only derivative couplings of this field to the heavy degrees of freedom. So the VF of the field cannot affect their masses, the spectrum will not change. The problem is that now you're either not inflating or you're inflating the whole time because the potential is really just a constant. So what you want to do is just break the shift symmetry in a controlled way, ideally by a single term. Then quantum corrections will still generate additional terms, but these terms must be small because they must come accompanied with a small parameter that went into the breaking of the shift symmetry. One such example is Linde's chaotic inflation, just m squared phi squared, as long as the mass is below the Planck scale, or the model of natural inflation, where the idea is to have an axion as the inflaton and use the non-perturbative contributions to the axion potential, which I'm schematically writing here as a cosine phi over f. to be consistent with the data, this currently requires that the axion decay constant is large compared to m Planck. And so in a field theory setup, you can just postulate this and it will be self-consistent, but it's really not obvious that these shift symmetries exist in a theory of quantum gravity. The only theory of quantum gravity to study these things is string theory. So when I here say theory of quantum gravity, I really, from now on, will mean string theory. And in the context of string theory, at least the most naive implementation of just having an axion with a super Planckian decay constant seems hard to realize. This was pointed out by Bang, Stein, Fox, Gorbatov a long time ago. And then there was a general argument that gravity should be the weakest force, which is not yet clear if it rules as well. For a single axion, it does. And there recently has been a lot of discussion trying to use this weak gravity conjecture in a number of papers, trying to see to what extent it really constrains large field models of inflation. But in any case, there is a strong motivation to study these large field models of inflation in the context of quantum gravity, or since it's really the only example we have where we can actually ask and address these questions in the context of string theory. So there's no systematic study. We haven't done it. As far as I know, no one else has done it. There's only a number of lampposts that people have been constructing. One of them goes by the name of axion monodromy inflation. So axion just means that the inflaton in this case is an axion. I won't talk in too much detail about where this axion is coming from, but if anyone is interested in these models in more detail, I'm happy to talk about it. Monodromy is what I'm trying to illustrate here. So monodromy means that you still have a field that or a system that's periodic. So you have here the axion has a potential that's periodic, but it's also multi-valued. So as you move out the axion from the origin, it actually moves up and becomes, once you're away by more than pi times f, you're on a metastable branch, and the idea is that you're inflating along these branches. So this is, and well, you might wonder if you're just tunneling down onto these lower branches, but it turns out, maybe not too surprisingly, that the classical motion along these is faster than the quantum mechanical tunneling. So this is the basic picture for these models. Monodromy really arises in various contexts, not just in string theory. It also arises in non-abelian gauge theory. So here what I mean is if you take a large n SUN gauge theory and ask what is the dependence of the energy on the theta angle, you find that you get monodromy, and it's periodic, but it will be a bunch of, it will also be multi-valued in that case. Similar things apply if you have light fermions and have some chiral Lagrangian. And the case that we've been using for inflation is in the context of string theory, where the axions become non-compact because of the presence of branes or the presence of fluxes, which is quite generic in these cases. Now, this is just a comic version of what this model is supposed to look like. So string theory, this is a model in the context of type 2b string theory, where all the moduli are stabilized in the same way as in the KKLT proposal. So that means you stabilize the complex structure moduli and the dilaton using fluxes, and you stabilize the Kähler moduli with non-perturbative effects. And the idea is that you have some six-dimensional bulk up here, and then this is the basic building block that is supposed to realize large field inflation. It's more of an existence proof, so it doesn't have to be pretty. It's definitely not pretty, but the idea is that you have a throat that comes out of this geometry, and then this throat bifurcates into two little subthroats. And I can say in a little bit more detail why it's supposed to look like this, but the axion, the inflaton here, arises from integrating the C2 P form, the C2 form in type 2b string theory over this 2 cycle, and it gets a potential because an NS5 brane is wrapping that cycle from essentially the S-dual, well, the S-dual of the DBI action. And then there's reasons to control the back reaction. This part has to be slightly higher. Anyway, so this is the comic version of these models, and if anyone's interested, I'm happy to talk about them more.
Explore that with you a little more.
Sure.
So you're saying that we're talking about a topological situation, but in a throat context, in a six-dimensional system.
Yeah.
So a number of years ago with Kaufman, we worked on, again, type 2B, and we were interested in essentially holes in the manifold.
Okay.
And so if you could have sort of not fully holes, but you could have something that has that kind of, I mean, this looks like, you know, an animal with an antenna or something.
Okay.
And so in terms of the geometry of moduli, is this something that you would guess would be pretty generic, sort of some kind of handles or something on the manifold?
Oh, the handles I think is very generic. Here we're asking for something that's so what we're asking for is really a one-parameter family of these two cycles, and you want there to be places in the manifold where they're just the sizes are minimal, and then away from those places it gets a little bigger, so the brain can actually sit there and not slide around. So this is the setup you should have in mind. So you have a
would there be any sense of an attractor towards those regions?
If you were to pull the brain away from there, yeah, it would fall back there. Yeah. So it's a little bit hard to draw, but these balls here should.
Betting on the probability of Axion monodromy, what would be your?
Okay, well, Axion monodromy in general, or this particular realization of it. I mean, there's more general versions of Axion monodromy by now. So I would bet 0 on exactly this realization. The mechanism, I think it's just difficult to say what's generic in string theory, but I think this, the basic mechanism of, we know that axions are fairly ubiquitous in string theory, and monodromy is too. So there's, whenever you have branes or fluxes, these axions will become, will have these multi-valued potentials. So this part, I would say, is fairly generic and is a good candidate. What makes it somewhat hard is to control the back reaction. So the story, for example, that I was telling earlier, that we want to have a small term that's breaking the shift symmetry, this is something, and then everything has to be proportional to this term. This is something that we were trying to realize. But this model doesn't actually realize this idea. So here, the potential that we're writing down, the dominant part from the potential, comes from the dBi action, and its tension is warped down because you're in this region. So that term is naturally small. But in this geometry, as you displace the axion away from the minimum, it also induces 3-brane charge on the 5-brane. And this 3-brane charge is not really warped down. So there's additional effects. And to control those effects, you make the model in a way that's getting contrived. And so ideally, you would like to find a model where large values are actually just natural. We don't have a model like that. You actually have to work to get it to work. And there's always, the back reaction always gets large enough that you, for example, can never get into the eternally inflating regime in these models. I don't know if that's a feature or a bug, but there's probably more general structures that we haven't yet found. So this is just one structure that we came up with. There's recently been more generic structures, but it's not clear that the most general stuff has been explored, I think. So I would say the probability for this individual model is 0. The probability for the mechanism, it's hard to say. I mean, we're pushing down on R quite rapidly, so we'll know more in a few years. But
yeah, but I mean, just because not everybody is as familiar. So the entire field of cosmology leaped upon Axion monodromy, and it was because it allowed R to be bigger to justify the experiments that we were all doing, because the standard folklore had been that R would be about 10 to the minus 10 in string inflation. So this has become a really big deal, and apart from the fact that there's been, well, excellent people have looked into this model in great detail, but you know, Planck has also taken that very, very seriously,
Yeah.
and it's got all sorts of exciting things to probe. And so the importance of the model in terms of an illustration of how to get large R and the consequences of it, I think it's, you know, it would be good to have a really good proof of concept that we protect it.
Yeah. No, I agree. I mean, yeah, I think there is still additional work to be done in these models in various ways, and hopefully relatively soon before the data tells us that we don't have to build them anymore. Right, I'm a bit worried because so this model is from 2009. This is something we worked on in 2009. So it's been a while since then. We've continuously been working on it, but it's not at a level where we can, for example, in any way say whether we think it's more likely to have large field or small field models of inflation, or even compare within. So Alexander Westphal has been trying to assess a little bit in a context where you can have both large field and small field models in the same setup, which one is more likely. And for him, I guess he finds that it's more likely to have something around 10 to the minus 3, which may be interesting for CMB stage 4 or some of these experiments. But I think it's difficult to say. For me, I still think they're interesting. I don't think the mechanism itself is contrived. What makes it difficult is really that it has to happen at high energies, and you don't have a lot of room between the Planck scale and the Hubble scale. So this is usually where the complication in the models comes from, not so much directly from the large field range here, I guess, at least.
And do you also just restrict to the Neveu-Schwarz sector of the or
Sorry?
Do you also just restrict to the Neveu-Schwarz sector, or
This is the Ramon-Ramon 2 form, so I wasn't very specific, but so in the DBI, if you look at a D5 brane, in the DBI action you get the determinant of the, well, square root of the determinant of the pullback of G plus B. If you take the S dual of it, you get C2 in there instead of the B2. So this is the axion that you get.
So this is a subsector in the Ramon-Ramon sector, right, which is the Neveu-Schwarz sector?
This is really a Ramon-Ramon 2 form. The axion that we're looking at. So yeah. Okay, so yeah, as I briefly already mentioned, so there have been more general constructions, and there's really a class of models that looks like this, where you have phi to the p, where so far people have realized these kind of numbers, but I think the idea is that you can really essentially choose p to be more or less what you like. So an additional example here was 5/8 that I actually forgot, but so the 2/3 was one of the first examples. There's also one in type 2b now. The linear, this is the one I showed you on the previous slide, gives a linear potential, and so on. And the additional prediction that comes from these models is that you might have oscillations. They come from, in this case, a Euclidean D1 brane that's wrapping the same cycle, and this would give rise in this model. So you have the linear model, and then you have these oscillatory pieces, and this is something that we've searched for, Dan searched for, the Planck collaboration has searched for, and I think it's interesting. We've been working on additional predictions of these models recently. So really in this larger class I mentioned, it looks a lot more complicated. So you can have running for the axion decay constants. The reason for this is that the axion decay constant is not really constant, but it's something that's set by the volume of a 2-cycle. And as inflation goes on, the volume of this 2-cycle may change, which means that the axion decay constant depends on the scalar field. Similarly, the amplitude of these oscillations also may depend on the inflaton. This is something one can still derive an analytic prediction for the power spectrum for. Looks like this. One can still look for it in the data. We looked for it. The Planck collaboration also looked for it. And here in this plot, what I'm showing is every dot is a point in parameter space that leads to an improvement over a lambda CDM of at least 4. And bigger dots mean larger improvements. The biggest dots here lead to an improvement of around 18 over a lambda CDM. The question then is what this means, and unfortunately it doesn't mean much, because if you do simulations that have no signal in them, you find that you expect something like an improvement of 16.5. So this is really not a significant detection of any kind.
Could you go back to the figure though?
Yeah.
So PF equals 0 is the standard case.
Yeah.
And it's clearly just a more or less continuous variation
Yeah.
with some. So what is the interpretation of those thick sort of black things along some of those
Here?
special lines? No, the ones that are beside it.
These?
Yeah, and the size of those and.
Yeah, okay, so the size, as I said, tells you how big the improvement over lambda CDM in the fit is. So the bigger ones have an improvement that's larger. This is one of the ones that's been seen since the WMAP5 data, this frequency, and it's an improvement of around 10 or so over lambda CDM. And then for higher frequencies, you get improvements that are as large as 18. The reason that you're not seeing a more dramatic dependence on PF here is that the range is relatively small, so the drift isn't too large. And larger F means that you have fewer oscillations in a given range of K modes. Right? And so the drift of the frequency is more easily seen if you have more oscillations. Because if you just have one long wavelength perturbation and that frequency drifts a slight little bit, it will still have large overlap with the initial one. So really, so one thing that we should do is increase the range on PF and also understand a little bit better what's going on at high frequencies where the drift matters more. Does that answer the question? No.
Yeah. So, but the changes are, what am I trying to say? Perturbative PF just takes you basically back down and slightly changed that. Is that correct?
Perturbative PF. So PF equals 0 is this?
Here is a phi that corresponds to, let's say, some K for large-scale structure. And then I'm interested in shape pretty near that. And so, often you can do an expansion around that.
Okay.
And that phi with the 1 plus p, where p is large or negative, I might have thought you could sort of maybe treat that somewhat.
Well, so we understand theoretically why there are these. That's why I've been putting these lines. So we understand what these lines are. Essentially here, these oscillations in this regime is just cosine of log of k. That's the only thing that you're really seeing. So this is what these lines are. So it's really you're just seeing, if you could expand it in terms of log k, and then you're seeing that here you're only sensitive to the first term or maybe the second in this expansion, but not more than that. As you go to higher frequencies, you're sensitive to more of them, and eventually that expansion breaks down. And I don't think that necessarily expanding in phi itself is good because you have several oscillations per Hubble, but you can expand in this log of k. Okay. So now I just wanted to say a few words about the B-mode search. And here I'm just showing the bicep data that most people, I think, must have seen. The excitement, of course, was that if you look at the E-mode maps, you see that the maps are consistent between what is seen and what is expected from simulations of lambda CDM plus noise. On the other hand, for the B modes, this wasn't the case. So if you just simulate the expectation for lambda CDM, you just get lensing B modes and noise, then you see that there's significantly more of a signal in the map than there is in the simulations. The question was, what is it? I think Dan already mentioned it, so I'm not spoiling anything. Unfortunately, most of this is dust. The maps are still very valuable because they really are the deepest maps of the sky at 150 gigahertz. The noise level is 87 nanokelvin degree, and you can compare this to a few microkelvin degree for Planck, and it's about 50 nanokelvin degree if you combine bicep 2 with the Keck array 150 gigahertz data. So they're still the leaders in the field, and they're very valuable. For me, I guess because I cared about these monodromy models, I wanted to understand exactly how large the contribution of R is, how much of it is dust, and there wasn't really any dust included in the likelihood by BICEP. So I started trying to make a foreground model for this, and yeah, so the longer I looked at it, the more I was convinced that I didn't really have to make a foreground model and make a new likelihood, because it was just consistent with all dust. I can say more about the individual estimates if anyone's interested in it. But in any case, so these were with David Spergel, Colin Hill, and Aurelian, who wasn't really in the end on the paper, but he gave me, for example, the starlight polarization data that we used to extract polarization angles in one of the estimates. And we also discussed it a lot with him. And he's on the Planck collaboration, so eventually he wasn't on the paper for this reason. But for a long time we thought he could be on it, so he asked Jean-Loup, and he said, yeah, it's okay. And then a day before, Jean-Loup said, oh, maybe I should ask more people. And then after that, okay, he wasn't allowed to sign the paper anymore. So this was later confirmed by the Planck collaboration. This was my little measurement, and this was for comparison the measurement from Planck. On the one hand, I was happy that they agreed, because this was a somewhat iffy measurement and it involved various things that I don't necessarily want to repeat. But so it was nice in the sense that it agreed, but it was also disappointing because it meant that it was largely dust. This is the current constraint, and from just a few weeks ago, from BICEP, Keck, including the 95 gigahertz data, and it bounced actually this should have been 1.7 now, but in any case, so this is the latest contours, and it seems like there isn't too much progress in the vertical direction. It's not too much better than what we had from the WMAP or the Planck data. So I want to briefly explain that that's maybe the wrong way to think about it, because we're actually constraining the amount of tensors in two different ways. So one of the ways to constrain the tensor contribution is from their contribution to the temperature anisotropies on large angular scales, where tensors essentially just add a constant. The other way to constrain it is directly from the B-mode polarization that they generate. The two likelihoods are essentially independent, so the joint likelihood is just the product of them. Typically, we're only interested in the case where the contribution to TT and BB is the same, so we're looking at the diagonal. But it's interesting to really look at this as a two-dimensional likelihood, because it then tells you how much of the constraint is coming from the temperature data and how much of it is coming from the B-mode data. And if you make this plot, what you see that before March, so before the BICEP 2 announcement, the status was this. So you had the bounds from Planck around the time, I think it was 0.13 at 95% confidence level, and then the constraints from B modes alone were around 0.7 from BICEP 1, and it was completely dominated by the temperature data. On the other hand, after March, this is what BICEP achieved. So it really shrank the error bars in the B mode direction by a factor of 7, and it just so happens that we're now at a stage where the constraints from B modes and from temperature are comparable, and so we don't yet see the improvement, but this improvement will now come very rapidly. So it will will shrink the error bars very quickly now with the help of various experiments. So here's the list of a number of them. I probably forgot some, but some of them you know. It's BICEP, Keck array, BICEP 3. Then there's SPT pole, SPT 3G, ACT pole, class, polar bear. I can say more about each of them, but this is just to give you an idea that there's really a lot of people searching for these primordial gravitational waves, a big effort. And there's also a number of balloons, EBEX, Spider, Piper. And in the future, hopefully we'll see the CMB stage 4 experiment, and hopefully also satellites, Lightbird and Pixie. Pixie, of course, isn't just a mission to look for primordial gravitational waves, but it's also supposed to improve on the measurement of the black body spectrum, look for spectral distortions, and you can do a lot of interesting science with this. So it's somewhat complementary, but will also provide good constraints on the tensor to scalar ratio. Here is just one plot that's showing the challenge. So this is the kind of signals that we might be interested in. So this is a tensor contribution to BB of 10 to the minus 2. It's about comparable to the lensing B modes from the conversion of E modes at that point. And here is the dusts in the roughly the cleanest 1% at 150 gigahertz. The reason I'm plotting it at 150 gigahertz because it's really difficult to know exactly how high it is. So it would be big bands if you draw it at 90 gigahertz. But at around 150 gigahertz, we still more or less know what's going on, and it's significantly higher. So that's really a big challenge, and hopefully this will be overcome. Another problem is, of course, that we don't really understand the foregrounds too well. So here is one way to illustrate this is just to take a patch of the sky and look at the histogram of the polarization fraction. This is the data, and these are the various models. So as you can see, this is the blue one is the Planck sky model. The other ones are these models by Carlo Contaldi et al. And so you see that they really don't describe the sky well at all. This also makes forecasting and various other things difficult. So that's basically all I had to say. And if you have questions, I'll be around until tomorrow afternoon. So thanks.
You had this idea about what the A lens that should be in the Planck aspect?
I don't really know for sure, but I'm wondering if it has to do with there's a lot of filtering going on to the time order data, which hasn't really been simulated end-to-end. The effect on cosmological parameters is not known. So I'm just saying that 98% of the data is affected by cosmic rays. 30% of the data is thrown out because of cosmic rays. One of the things I'm trying to understand, for example, it seems to not be there in polarization. So one of the things I've been looking at is to what extent the spiderweb bolometers and polarization sensitive bolometers are affected differently, if there's any differences between them. I was told that Planck hadn't done analyses independently for spiderweb and polarization sensitive bolometers. I don't know if that's... You have now, or? Oh, okay. That's something anyway, I don't know. And the other thing I was trying to look at is, if it were something like this, you would expect the effect to depend on time. So one thing you can do is you just measure the angular power spectrum along the rings, and then you see if this varies with time, essentially. There's a lot of things one has to include, like asymmetric beams and whatnot. I mean, a lot of systematics that might lead you to think you have a systematic when really you don't. So this is something I've been doing. It's a little bit tricky because I don't have all the simulations. It would be great if all the simulations that Planck has were actually publicly available. Then it would be much easier to do. But right now, the only ones that are available are the full mission simulations, which means you have to worry about the noise bias and so on. So it just would be great to have more simulations to check it quicker. But
so would you expect a lot of those things to affect the 4-point lensing measurement too? Because there's this 2 sigma tension between the lensing and the 2-point and the 4-point.
Uh-huh.
And it's all coming from the same data. So anything like that, I guess, might affect the 4-point.
Yeah, I think so.
So that doesn't solve that?
Well, it's not clear if it will affect it in the same way. To me, it's just not clear. It's just something one has to check, but I don't know. I don't know if there, I mean, so I can see here why you might smooth out the peaks. I don't know why it would also lead to, because this A lens is not a very physical parameter in this case, right? It's just measuring some peak smearing. I don't know why it should lead to high A lens in the 4-point function is all I'm saying.
But it's the same effect that the 4-point measurement is latching onto, so again, it affects the 2-point, probably using the same way.
It's not obvious to me, but it could be.